Right, so this is lecture 34. Today we will talk about GPU architecture. So as we said that it's very important to understand the architecture in terms of the memory, because memory can become the bottleneck in many a times, and it's very difficult to realize that because it's not as intuitive as understanding the bottleneck in terms of computations. So the aim of today's lecture is to understand the architecture of GPUs in terms of memory architecture, and then once we understand that, we will briefly talk about through an example as to how to organize your data and how to position it in the different memory structures available for efficient access. Okay, so that's the second step. I mean, once you understand the architecture, you have to use that information to the best of your utilization. So sorry. So there is a global memory that is something that we have been talking about. It's an off-chip memory in the sense that it is not on the computing chip in the GPU. So it's far away on the GPU card from the cores as compared to an on-chip memory or on-chip memory structures which are closer to the computing cores. So we also call this global memory or the off-chip memory as DRAM in GPU. So when you buy GPU cards, you will see some memory like a 16 gig card or a 24 gig card or a 32 gig card. So that's the global memory that is being talked about. So the characteristics of global memory are: one is long latency. So it's typically hundreds of clock cycles which are needed to be able to access the memory. So I'm sure you understand the latency as we talked about in the cache as well. When we have to move information from a farther position, then it requires some clock cycles to do that. So this is like a transient situation. So if you request something, it takes some time for the information to percolate further and then come back to you. And also it has a low bandwidth. So bandwidth is once the information transfer has started, the rate at which the information can transfer is also limited. It's like if you have a water pipe, how large is the diameter of the pipe? So that's your bandwidth. If you have a smaller diameter, small amount of water can flow per unit time. If you have a larger diameter, more water can flow per unit time. So bandwidth is also limited for this global memory. And sometimes because of a lot of demand of global memory at different cores, because global memory is accessible throughout the GPU. So that means all parts of GPU, all streaming multiprocessors can request this global memory. So if they do that, then there can be congestion in the global memory paths which are used to connect them to the streaming multiprocessors. So this can have a large wait time. So the message is that global memory has constraints, and if possible, if we can move the information somewhere closer than global memory, then the memory bottlenecks can be avoided. An on-chip memory, as I said, which is closer to your actual computing cores, can avoid all these issues because they have lower latencies, because they are much closer to the cores. They have higher bandwidths, okay, and one does not have to wait for information to be transferred from this on-chip memories to the compute cores. They do not have to wait a lot because they are only accessible to the streaming multiprocessor. So the users, the number of users of that memory are small in number. Right, so let's talk about something called compute to global memory access ratio. So earlier we had briefly touched upon it, that there is an amount of computation you are doing and there is an amount of memory access that is required for a given algorithm. So you ideally want to minimize the memory access and maximize the computations, because if for one unit of computation you end up moving a lot of information through the memory, that's not very efficient. So intuitively we understand this idea that you move a very small amount of information and try to do as much computation as you can with it. This will be more efficient. So let's quantify this idea. So let's have a look at the matrix multiplication kernel. I mean, just a snippet of that we had seen earlier in the previous lecture. So this is where we are multiplying matrices. So p value which is storing the information of the sum of one row multiplied by one column. So that's one element of the resultant matrices being multiplied. So m times n is equal to p here. So you multiply one row of m with one column of n, and k is the index that allows you to move through different elements in the row or the column when you are doing the multiplication. So if you look at one iteration of the loop, that is multiplying one element of mth row, m's row with one element of n's column. It requires two global memory accesses, because remember this is stored on the global memory. So you have one access for the element of m and one access for the element of n. So that is for one iteration of the loop. You have two global memory accesses and you perform one multiplication, and then there is one addition also involved with that. After multiplying the elements, you add it to p value. So there is one floating point multiplication and one addition involved. So what is the compute to global memory access ratio? You are doing two floating point operations, so two flop, and you are moving two memory, or you are having two memory accesses. So in this case we are using a single precision. So float is a single precision 4 byte real number in C++. So that is to 4 bytes plus 4 byte, that is 8 bytes. So this is two floating point operations per 8 bytes of memory moved. So that is 0.25 floating point operations per byte, a flop per byte. Okay. So this is very easy to quantify seeing the algorithm. Now let's look at an example. So A100, NVIDIA A100, which we have been talking about a lot, has a peak bandwidth of 1,555 gigabytes per second. So bandwidth is how fast information can travel. A peak is the maximum, you cannot go beyond that. So in most situations typically you will be lower than that, but let us say peak is 1,555 gigabytes per second. So that is the rate at which information can transfer from the global memory to your compute cores, and you have 0.25 flops per byte. So 1 byte of memory moved is doing 0.25 floating point operations, and you can move 1,555 gigabytes per second. So if you multiply these two numbers, you get the gigaflop per second or gigaflops. So this gives you 389 gigaflops for this algorithm. Okay. So in the present algorithm that you are using, you can do a maximum of 389 gigaflops. That is 389 times 10 to the power 9 floating point operations per second. And this is constrained because of the bandwidth of memory that you have here, 1,555 gigabytes per second. But actually if you look at the card specifications in A100 NVIDIA card, you see that the peak throughput of A100 is 19,500 gigaflops for the CUDA cores it has. So because of this memory constraint, you actually went down 50 times. So that is a huge loss in terms of throughput. I mean the card can do 19,500 gigaflops, but because you have an algorithm which is doing very small amount of computation per unit memory access, and memory access is limited bandwidth because of the constraint of memory. So that is, you are getting only 2% of what the actual card can give you in terms of gigaflops. So these kind of programs or situations are called memory bound programs. It is not bound by the compute constraint, it is bound by the memory constraint. So now we have to think of what is the, if you have to redesign the algorithm, what is the ideal floating point operations per byte we need to be able to utilize this complete 19,500 gigaflops. So that of course is 50 times of this, so that is 12.5 floating point operations per byte is what you need to do this, to utilize this 19,000. So you are using 0.25 flops per byte and you need 12.5 flops per byte. Okay. So if you think of if you are using 8 bytes like in this case, then for those 8 bytes you will have to do 100 flops. I mean 8 times of 12.5 is what you will need to be able to do in the algorithm to fully utilize the compute power of this GPU card. That is 19,500 gigaflops. So it is very important, and you should be able to calculate this number, which is the compute to global memory access ratio. So we have the compute, you calculate for a given algorithm for one step, of course I mean multiple steps are just a multiplication of that, so the ratio does not change. So how much of a computation you are doing in a given step and how much of a memory access are you doing in that given step, and you take the ratio of the compute to memory, that gives you compute to global memory access ratio. Remember, it is global memory. Of course, I mean if the memory was closer to the, or the memory was on chip, this would not have been there. So basically what we want to do is we want to redesign our algorithm so that we can move the information from off chip, that is global memory, to on chip memories available which is closer to your core. So for that we have to understand the different types of memories available with us, so that we can decide where to move the information, and this is where GPUs or CUDA programming becomes a little more complex than CPU programming, because you have to explicitly decide on which memory is the information going to sit. So let us have a look at the architecture of the memory in terms of memory. So what we see is that these blocks are your streaming multiprocessors, or let us say it is basically a block sitting on an SM, and then rather let us say block, not streaming multiprocessor, because streaming multiprocessors it is a different idea. So let us talk in terms of blocks. Okay. So the memory which is farthest away is your global memory and constant memory. So we will talk about what they mean, but let us talk about what they are first. So you have global and constant memory, memories which are farther away, furthest away from your compute cores. Then if you look at a block inside a streaming multiprocessor, you will have something called registers. Registers are closest to your compute cores, and then you also have something called shared memory. So shared memory is also available on chip. So this is much faster as compared to global memory, but it is different from registers. So let us talk about, let us understand what these are. So global memory is something we understand. So global memory is the one which is, I mean if you remember when we wrote our vector addition program or the matrix multiplication program, what we did was the first part of the program was to allocate some space on the global memory, and then we copied our data structures from our host memory to the global memory. So, global memory was definitely writable by the host. The host could write to it and the device could read from it. Okay. So, that is what we have mentioned here, that the device code can read and write your global memory, because you saw in the program we read from the global memory, and when we had the answer available we had written down to the global memory as well, and this was happening from the device. So, your GPU cores can read and write from into the global memory, and the host can also read and write from the global memory, and that is what the host did as well. In the first part, the host copied the information from your host memory to the global memory. So, that was writing to the global memory, and then in the last part the host read from the global memory. So, the host could read from the global memory as well. So, global memory is where everybody can read and write, okay, and that's the intent of global memory. Now comes constant memory, which we haven't talked about till now. So, constant memory is a little shorter in terms of latency, and it is a little higher in terms of bandwidth as compared to global memory. But the only difference is it can only be read by the device cannot write to it. It is the host that can read and write to the constant memory, but your device can only read the constant memory, it cannot write to it. So, one benefit of this is that if the device cannot write to it, it is structured in such a way so that it is a little faster. Think about it, if the flow happens only in one direction, you can make things much faster. If you want the same thing, same pipe to allow flow in both directions, then things get a little slower. Okay. So, this is constant memory, but again it's near your global memory in the sense that it's not very close to the chip, it's still off chip. Then we talk about something called local memory. The local memory is another kind of memory which actually sits on the global memory. So, some part of global memory, physically speaking, is allocated to something called local memory. But the difference is that local memory is allocated to threads. So, in the next slide we will talk about the scope of these memories, but local memory is some part of global memory which is allocated to each and every thread. Now, remember, global memory was available to in a shared sense to all the threads, all the cores, but local memory is when you want private memory for each thread, but it is not available on chip. So, what you do is off chip on the global memory you allocate some memory, but one unit of memory is always available to one unit of thread, it cannot be shared. So, when you do that kind of a mapping, that memory is called local memory. So, if for example, like in a kernel function, if you remember, there were variables like we had idx or id or I. So, these variables were private, what we call automatic variables. So, if instead of an automatic variable you had an array, a static array in the kernel function, that static array will be allocated on the local memory, that is on the off chip global memory, but allocated only to that thread. The other situation is spilled registers. I mean, if the registers are full, then what do? If you want private memory for threads, but there is nothing available, no space available on registers, all you have to do is you have to move to the global memory, but in that case we call this local memory because it is a part of global memory which is only available privately to threads. Okay. So, this is off chip Three kinds: global, constant and local. Now we come to on chip. So on chip we have two kinds: registers and shared. Now the good thing about on chip is it is much lower in terms of latency and much higher in terms of bandwidth access. So this is where you want to keep the information as much as possible. So the first is registers, which are by definition private to threads. So if a program allocates some registers to a given thread, then only that thread can access those registers in the program. No other thread can access those registers. So what are they used for? They are used for automatic or kernel variables. So if you have variables that you declare in your kernels, they automatically become private variables which are allocated on registers, and these are 100 times faster than your typical global memory. And now is something which is the most interesting, is called the shared memory, which is what you see here in the block. So shared memory is a memory which is shared, which is on chip, so it's much faster, but it's shared for a block. So all the threads in a block share their own block shared memory, which is called the shared memory. So that is the reason you see that there is a block here and there is a shared memory. So all the threads in the block will be able to access this shared memory. But if you see registers, each thread has its own registers, although they are also there in the block, but they are private. So if thread number 1, 0 wants to access this register, it cannot do it. Somehow the information has to move to the shared memory, and then is when this thread 1, 0 can access this information. Now because you have such a such a hierarchy of memory, and the user actually has control over where to move what, and that is where things become interesting. So let us have a look at this. So we talked about different kinds of memories. The let us move from here. So constant memory, global memory, shared memory, local memory and registers. Okay, although local, global and constant were off chip, and shared and register are on chip, but they are not ordered in that way. But with the memory, we are also talking about how to declare them, how a user or a programmer identifies where a variable goes to. So you have some identifiers to identify where a variable, or a keyword to identify where a variable will go, but we also need to understand the scope of that variable. So for example, if you look at registers, registers are utilized when you allocate automatic variables in kernel functions. So these kernel functions, registers are private to threads. So the scope of this variable is thread. Only a thread can access a register. The other threads cannot access that register. Okay, so that's the scope of the variable. And then there's a lifetime as well. So whenever you launch a grid through a kernel function call, registers are allocated depending on requirements, and once the kernel execution is finished, the registers are freed. So this is your lifetime of the registers. Okay. So how do you allocate or declare or what is the keyword for registers? I mean, they are automatic variables. So if you have a kernel function and you declare a variable there like int I inside a kernel function, I automatically becomes or gets allocated on the registers. Now let us come to local variable. So local was an off chip. Remember I said when registers is in the case of spilled registers. So if your registers are full, then what the compiler automatically will start allocating that information to your local memory, which is actually sitting on the off chip memory in the global memory. So the scope is still thread in the sense, because it is allocated for each thread privately. So the scope of local memory is also thread, and the lifetime is also grid, because once the execution of that kernel is finished, the local memory is also freed up. So it has the same scope and lifetime as your registers, except that this is allocated on the off chip memory. And when is it used? One, when you have static arrays, because arrays typically are large, so you don't want to waste a lot of information on registers. And the other is spilled registers. If your registers are full, then the compiler has no choice but to start using the local memory for private memory access to CUDA cores. Next is shared. So shared memory is, if we go back, is this memory which is on chip and is accessible by a block. So the scope of shared memory is block. So all the threads in a block can access your shared memory, and the lifetime is still grid. So once a kernel function execution is completed, all the shared memory is also freed up. And how do you declare a shared variable? You simply use the keyword underscore underscore shared underscore underscore that makes the variable shared. Next is global memory. So global memory is, the scope is grid, because all the threads in a given CUDA card can use it. So all the grid basically comprises all the CUDA cores, all the threads. So the complete grid can access your global memory, and the lifetime is application. So if you copy information from host to device, it sits there until you free it. Okay, so that means the lifetime is the complete application, not just your grid. And finally, the constant memory, which is basically used when you simply want to read information into the device. You don't want to write anything from the device. So it still has the same scope and lifetime of the global memory, but to declare that, you use this underscore underscore constant underscore underscore keyword to identify them as variables which are constant. Now, when do you use shared variables? So if you have a portion of data which you are using again and again, and you don't want to access the global memory for that, but that data is still supposed to be shared. If multiple threads want access to some data collectively, then if possible, you will move that data from global to the shared memory, so that you don't waste time trying to access the data again and again. So let's look at an example, and in this example we will actually the aim is to reduce the compute to global memory access ratio, because that will help you utilize more computing power of the card. And for that, what we will do is we will try to redesign the algorithm so that we can move some information from global to shared memory, so that threads which collectively want some information don't have to keep accessing the global memory, because global memory is off chip. So the example is still matrix multiplication. So in this case, what we do is, what we are doing is we are multiplying m and n to give you p, and this is the same as what we had discussed last time in terms of the matrix multiplication example. So to calculate p00 element, you take the 0th row of m and the 0th column of n, and you multiply them with each other, right. So what we do is, for this, the way we are redesigning the algorithm is we break or we split the p matrix into tiles or blocks. In this case we are using the word tiles because blocks is reserved for GPU blocks, but we have discussed this example briefly in our CPU based parallelization as well, remember, when we did block multiplication of matrices. But I will assume that you don't remember that, so let us do it afresh. So you break your p matrix into tiles. In this example demonstration, what I am doing is I am breaking it into 4 tiles. So this p matrix has 4 rows and 4 columns, and I break it into 4 tiles. So each tile, I am showing one of these here, is going to have 4 elements of the matrix. Okay. So you have a so each tile is 2 by 2. Each tile has 2 rows and 2 columns, and what you do is you let each block in your GPU structure deal with each tile. Alright. Of course, I mean 2 by 2 is just an example. It can be 8 by 8, it can be 16 by 16 depending on different constraints, but for this example I am showing right now you do not need to worry about how to decide the number of elements in the tile. It is more you want to understand what benefit do you get out of this. So, you have 2 by 2 tiles. So, now let us look at in this 2 by 2 tile, if I try to calculate P00, which is, so each thread calculates one element of the tile or the matrix. So, thread 00 requires to multiply M00 with N00, and then you multiply M01 with N10, M02 with N20 and M03 with N30. So, this is what we have written here in all the elements that you need to multiply. So, if you look at one tile collectively, what you see is M00 is used twice, and that makes sense because M00 is used when you calculate P00 and you calculate P01. So, every element is accessed twice, or every variable is accessed twice in a tile, and whenever you need this you have to request this from the global memory. So, if somehow we could move all the elements that we have here onto the shared memory, then we could reduce our global memory access by half, right? Because M00, if it is sitting on the shared memory, then you only access it once to copy it from global to shared memory, but if once it comes on the shared memory, it is so quick that you do not even count that, because compute to global memory access ratio is what matters. Shared memory access is so fast, it is negligible as compared to the global memory access bandwidth. Alright. So, the strategy is we will give each tile to a block, and the block will do the computations for each tile, but somehow we have to move the information from the global to the shared memory. So, this is where the threads will collaborate with each other by sharing information on the shared memory in a given block. So, this was an example of 2 by 2 tile which reduced or which resulted in the reduction of the memory by 2 times, that is half. If you had 3 by 3 tile, think about this. So, if you had a 3 by 3 tile, let us see if I can draw this. So, if your tile was something like this, I am using the mouse pointer, so it is not that neat. So, you see that then you will require M00 3 times, because this row has to be used for each element P00, P01 and P02. So, if I could move my information from the global to the shared memory, in this case reduction would be 3 times, it is much better. If I have a 4 by 4 tiles, it is 4 times. If I have an n by n tiles, each variable is used n times. So, if I move the information to shared memory, it is a lot of, it is basically 1/nth of the time the global access that you will need. So, things will become n times better. Of course, I mean you can't keep increasing this because your shared memory is limited. You will say that then all my matrix, the complete matrix sits on the shared memory, but that is not possible. If that was possible, then you will do it. But that is the thing, global memory is slow, it is farther away, but it is larger, like caches. If you come close, when you come closer and closer to your on-chip memory, they are expensive, they generate more heat, and they are much smaller in size. So, let us look at the program to understand the algorithm now. We have to pay attention here because it is a little it's a little subtle, so you have to don't miss the crux. So, the idea is that we have to load data from your M and N matrices, because this is where the global access is happening. You have to load some information from M and N matrices into the shared memory for a block for quick access, and each tile is being accessed by or handled by one block. So what you will do is you will work in phases. So you have two phases here, one's phase 0 and one's phase 1. In this example, of course, I mean you may have more phases depending on situation. So in the phase 1, all threads will do some data copying, and the easiest thing to do is thread 00, which is basically handling element P00. It copies M00 and N00 into the shared memory. So each thread has two jobs. One is to do the copying and the other is to do the computations that it requires to do. So thread 00, the first step is, now the direction of time is from left to right, by the way, in this case. So all the things which are in the same column in this diagram are happening at the same time. So each thread is copying two elements M00 and N00. So thread 01 copies M01 and N01, thread 10 copies M10 and N10, and thread 11 copies M11 and N11. So basically if you look diagrammatically, then in this phase number 0, thread I mean all the threads together have copied this tile. So this is M00, M01, M10 and M11, and it has also copied this tile into the shared memory, and shared memory is what we are calling in this case MDS, just a name of a variable. Okay, so M is for M, D is for device, and S is for shared. So M on the device's shared memory, so NDS. Similarly MDS 01, NDS 01 and so on. Okay. Is this clear? So this is where all the threads do the copying. So after copying is done, these two tiles which I have highlighted with the red box are now available on the device's shared memory. So the block which is handling this these four elements in the tile of P have access to these two tiles for M and N on their shared memory. So now what you do is, for thread 00 which needs to calculate P00, it uses these elements M00, M01 and these elements N00, N10 to calculate some part of its multiplication. Okay, and all the threads do that, because if you look at each thread, the way block multiplication works anyways, so you use these two blocks to calculate half of the work or do half of the computation. And now you move to the next phase. So the next phase, you don't need these blocks anymore. So now in the second phase, what you do is, each thread copies an element of M. So you get these four available in the shared memory and you have these four available in the shared memory. Now the remaining work is you further, so P value is a by the way automatic variable, it is a private variable, it is on a register for each thread, because each thread has its own multiplication. And then once these are available, now you use this to calculate the remaining part of the multiplication. So after these two phases, you have the complete multiplication available, and you reduce the work to half in terms of copying information from the global memory. So this is the algorithm which is much efficient. Let's look at the code. Give me a couple of minutes, we'll have a look at the code as well. So first we define the tile width. In our example it was 2 by 2, so tile width was 2. In this code that I am demonstrating to you, it is 16. It's more practical. Then you have the kernel call. Okay, you put a global before the kernel because it's a kernel function. You pass in M, N, P and width. Okay, width is the complete matrix width, not the tile width. So the complete matrix is the width of width, and then you have to declare these variables which are shared variables, that is NDS and MDS, which are going to store those two tiles for M and N on the shared memory in the block. So you have to put the keyword shared before that. So once you do that, each block allocates this amount of memory, and the size is tile width by tile width. Okay. So you see that in each phase, if I go back, you are reusing the tile memory. So MDS, you don't have a separate MDS for this part of the tile in phase 1 and this part of the tile in phase 2. You end up using the same space, because in the second phase you don't need the previous tile of M and N anymore. So it's all about using the memory effectively, right? Then you simply have block ID, thread ID and so on in x and y directions. You put them in some local variables, that's no problem. Then you have and remember, this code is a kernel code, so it's running on each thread, by the way. So each thread calculates its row and column it has to process. Then you're going to start with a phase loop first, and in each phase you work with some computation that we discussed. So this is simply a program for whatever we have understood in the previous slide. Okay, so algorithmically you are not learning anything new. So this outer loop starting in line number 16 is for phases. So in our example you only have 2 phases, so the loop will execute twice. And how do you decide the number of phases? You basically take the ratio of width, which is the total width of the matrix, to the tile width. So in our case, in the previous case, you had the width was 4 and the tile width was 2, so you had 2 phases. If you had a total of let us say 6 by 6 matrix, so you had 6 as the width and tile width was 2, then you will have the phases as 3. And now is where you each thread, because this code is being executed by each thread, so each thread copies one element of M and one element of N into the shared memory of the block. So it's straightforward, but if you move to a different phase, then you have to add just a constant depending on the phase number. So that's the reason you have this phase times tile width. I'm sorry for this spike, it's coming because of the mouse. So once you have, I'm going quick because you already understand the algorithm, you can read the code yourself. Then once you have copied, let's go back. So once you have copied all these, you have to have a barrier here, because all this information, so if you look at thread number 00, thread number 00 requires MDS 01 and MDS 01 is being copied by thread number 01. Similarly, thread number 01 requires MDS 00, which is being calculated by thread 00. So they are collaborating with each other. So what one thread needs is being copied to the shared memory by some other thread. So you have to put a barrier here, like you had barriers in OpenMP and MPI, is called sync threads here. And remember, barriers only work between blocks, between threads of a block. If you put a barrier, all the threads in a given block will wait for each other, but between blocks there is no barrier. So the algorithm has to be such that the barriers only are required within the block. So this is called a read after write barrier that I have written here. So that means once everybody has written to the shared variables, only then you start reading from it. Okay. So once the barrier, all the threads in a block have reached the barrier, they start, you start using them to do the calculation for calculating p value, as we had shown in the figure in the last time, and then you do a sync threads again, and this is called a write after read barrier, because once a thread is done using the memory, it again will start writing for the next time, but you don't want to do that until all the threads have done using that memory, because it may happen that, for example, one thread is done, it starts going to the next tile and starts copying into the shared memory, but a previous thread is already using it. So you have to have another barrier here to ensure that all the threads have are done using this memory in the shared memory, so that you can start utilizing the same memory again. If of course you were using a different memory, then you don't need to put this barrier. Is that clear? So that's pretty much a program that you will have to make the program more efficient, right? So we will stop here, and I'll do a brief recap of this next time. but I'll also talk about some savings that you can potentially get because of this, and some ideas about occupancy in terms of memory, and I'll also run the program and show you through comparisons between this and the program that uses complete global memory and see profiling between the two codes. Thank you.